All right, well, it looks like we have a quorum to get started. So thank you everyone for joining our seminar here. And we're very pleased to have Dr. Surja Sharma to give our presentation today. It's going to be one of the final presentations, I think, of this year for our seminar series. So with that, Surja, feel free to start the screen sharing as I give the introduction for you here. So yeah, Surja will be talking about data-driven modeling of the magnetosphere, the complex systems perspective. And Dr. Sharma has been engaged mainly in the theory, modeling, and simulation of plasmas, including both laboratory and natural plasma systems. His recent interests include the complex systems approach to modeling of extreme events, plasma turbulence, and machine learning. His synergistic activities include serving as the chair and president of the AGU Nonlinear Geophysics Focus Group, and also giving the 2009 AGU Nonlinear Geophysics Lorenz Lecture. So with that, as you're getting set up, feel free to take it away, Surja, and we'll ask questions. Questions can be in the chat, and we'll share them with our speaker at the end. So.
Okay. Do you have my
yes. Yes, everything looks good.
Okay, great. Greetings across the different time zones. I will be talking about the work we have been pursuing for some time now, mainly on the complex systems or dynamical systems based modeling. And I'd like to acknowledge, before I start talking about the topics, many contributions by my colleagues and students, in particular graduate students. Some of these contributions I'll try to identify during the talk. The presentation is motivated or maybe even triggered by the recent Nobel Prize in Physics for groundbreaking contributions to our understanding of complex physical systems. So I'll start my presentation with a very brief introduction to the achievements or the modeling of atmospheric and related phenomena. Then I will go to the data-driven modeling of complex systems in general and its application to magnetosphere or space weather. And from that, I will move on to the multi-scale nature of the magnetosphere, which makes the prediction very complicated, and then take the paths to prediction and predictability of extreme events. I will look at the solar wind turbulence as a complex systems, as a new approach to understanding turbulence, and present some ideas or preliminary results from machine learning in dynamic systems, and touch upon Geospace Digital as the twin of the actual geospace as a way to understand and excuse me, and develop predictive capabilities. Complex systems, of course, has many definitions or ways to express. One of the ways is to recognize that it has many independent components, and interaction among these lead to organized as well as irregular features, very familiar in the magnetospheric community. And also that knowledge of parts does not necessarily lead to the predictable behavior of the entire system. And such systems are widely referred to as nonlinear dissipative systems, which have dynamical behavior. In dynamical systems community, they are referred to as strange attractors. They exhibit chaotic behavior, and over larger scales, they show scaling behavior of some kind. And since they are treated as dynamical systems, we can model their dynamics and thus provide a way of making predictions and further of quantifying the predictability. And such systems are very common. We widely talk of Lorentz system. Magnetosphere is such a system. The Earth's weather and climate, a spin glass, which we will talk about a little bit. And these studies are not done in a coherent manner because of the different applications, but the underlying theoretical or formal framework has been developed since the early 1900s, or rather late 1800s, by people like Beltrami, Poincaré, etc. So they have sound theoretical foundation, even though they may not be evident from the general way they are presented or applied. So we mentioned about the Nobel Prize in Physics. It was announced last month as usual in October, and it is for physics for climate and other complex phenomena. And this is an interdisciplinary team, and it's not rare. It's rather not common to have Nobel Prize in such interdisciplinary or uncommon fields. And this prize was divided into two parts. First part was on the modeling of the Earth's climate and how humanity influences it. And this highlighted the work of Sekuro Manabe and Klaus Hesselmann. The second part is on the theoretical aspects of complex systems, given to Giorgio Parisi, who worked on disordered complex materials, whose understanding led to deeper understanding of complex phenomena. And many of these things are relevant to heliophysics as we go in some detail. Now, the Earth's atmosphere, for which the main component of the Nobel Prize was announced, is a very thin layer above the Earth, about 10 kilometers thick. As we all know, it consists of mainly of molecular nitrogen, oxygen, and some other elements. And it is heated or driven by the sun's rays, as is shown here, that hits the ground and the surrounding air. And the ground emits infrared radiation, and that propagates out into higher altitudes. And some of that gets reflected by the atmosphere. So there is exchange of energy between the air at different levels, and the hot air goes up because they have more energy content, so they rise, they're lighter, and when they reach a certain height in the atmosphere, they condense into clouds, releasing the latent heat, so they cool down, and then the cold air comes down and there is circulation. This is the picture of Manabe's climate model, in which he studied the vertical transport of air convection in the atmosphere and interaction with the radiation. So the radiation balance and the circulation leads to mixing, and that mixing leads to the equilibrium or the system in which the certain temperature is maintained. Now, including other components of the magnetosphere, such as CO2, is what was the main effect. And as we see here, if we look at the profile of the temperature, as we saw here on the horizontal axis, and with altitude, what is shown here is the temperature, and the effect of carbon dioxide at certain values, say 300 parts per million, is given by this dark line. And if you reduce the in that by half, then we get this light blue line. And if we increase, we get this red light increased by double. And the effect at the ground is opposite, or near the ground is opposite. The temperature increases. So this is the effect of carbon dioxide, which is referred to as the greenhouse effect. And so in this model, it becomes clear that the carbon dioxide leads to greenhouse effect. The question, of course, is how to model or how to understand the role of the carbon dioxide or other greenhouse gases. And this was achieved partly by modeling the sea surface temperature anomaly, or the variable X, in terms of a generalized Langevin equation referred to as the Ornstein-Uhlenbeck process. And in this model, Hasselmann used the weather or the noise as the noise on a short time scale to drive the sea surface temperature, which is a climate variable or changes over longer time scales. And so this is a way of making sense of noisy data or the multiscale nature. And this led to understanding of the observed sea surface temperature anomaly, as is shown here in the North Atlantic. And this also led to an understanding of the observed changes in the temperature. As is shown here, the dark line is the observations, and the red line is from the model in which the sources of carbon dioxide and other greenhouse gases from natural as well as human sources are included. And if we exclude the natural source, keep just the natural sources, that is the volcanoes, then the model shows this blue line or teal line. So this clearly shows that it is the human sources or the sources which are not natural that is leading to the increase in the temperature. Now, the underlying this analysis is the theory of complex systems or complexity of disordered systems pursued by Giorgio Parisi. And in this, he studied the spin glasses in great detail. In condensed matter physics, spin glasses is a very widely used model in which we have a lattice of copper atoms, as is shown here on the grids, the blue dots, and impurities of iron at random places, as is shown by the red dots. Sorry. And when we have such random distribution of impurities, one of the issues or a complicated question to answer is how would their spins be oriented, as is shown here. This is on the lattice, and this is the nearby lattice, and they have opposite spins. But when another spin comes to this lattice or a grid, whether it will be oriented in this up or down, and that is referred to as frustration. And there has been many theories developed and it was George Parisi who recognized the hidden patterns and developed a model for the spin glass and the symmetry breaking that lead to the evolution of such systems. This looks rather theoretical, but it has applications to weather and climate, biology, neuroscience, mathematics, machine learning, and that is a very useful or widely used framework for modeling these natural as well as other systems. Now, in heliophysics, the data-driven modeling has been pursued in a few teams. One is for modeling and prediction, which I'll go into some detail here, and that leads to dynamics and understanding of structure, essentially the spatiotemporal structure of the magnetosphere, and it gives us a way to quantify variability. And recently we have been working on machine learning and artificial intelligence using this framework. And much of the work in modeling and prediction was presented in the Lawrence lecture as shown here. And if those who are interested in the details can find good details in this. I will have to be brief in this talk. And let me start by showing how the reconstruction takes place. If we have a system which is as in this space, its dynamics is often described or represented by some trajectory on a manifold, on a surface. And when we make measurements, such as seen here, we make measurements of one or a few variables. So the question is whether we can represent or understand the system completely from these few variables, one or a few variables. The embedding theorem or the reconstruction of dynamics tells us that it can be done. And so if we reconstruct the dynamics from a single variable using this approach, then the reconstruction is diffeomorphic in the sense whatever the trajectories or dynamics is present in this actual system is in the reconstructed system. This is the basis for the reconstruction of dynamics, and the underlying theory is the embedding theorem. So if we have a single time series X, from that we can create many other variables X sub K using a time delay tau, which we have to choose carefully for the system. And once we have many vector components, we can construct a vector, and this vector is the space in which the dynamics will evolve. This dynamical modeling is essentially for nonlinear dissipative systems, and it has the theoretical foundation provided by embedding theorem and the dynamical systems theory. And this led to the development of the predictive capabilities for space weather, and US national report long ago was written on this approach, as were published in the reviews of geophysics, and the more later review is the review by Vassialiadis in the same journal. Now, we talked of dynamical modeling through the trajectories, and if we have the trajectories, we can make prediction, and the prediction is broadly done in a manner described here. We take a point now, which is here, and then define a space around it in which many trajectories pass through. And knowing the neighbors of this current point, we can make a model of how this current point will go in the next time step. And this is expressed in this fashion when we apply to the magnetosphere, which has the input as the solar wind and the output as the geomagnetic indices or some other variable. And when we look at the quality of the predictions, such as here, if we have the prediction for which is in the red compared to the actual value, and look at the mean square errors, then they have a minimum at some low dimensional or low value of the embedding dimension, or the number of dimensions of the space that we created. These studies were done by many. The singular value decomposition, which created the proper reconstruction of phase space, we started in '93. Sasha Korsky pursued it during his PhD period, and so did Jian Chen and many others. So with this prediction, we can develop a space weather forecasting process in which we have the solar wind as represented here, the induced electric field. And if we look at the data of AL, we have many values corresponding to a single solar wind condition. And with the dynamical predictions, we can make predictions as is shown by the red line, and the blue line, sorry. Blue line is the actual. So it captures the trend, but it doesn't capture all the big effects or these extreme events, which is not too surprising because the dynamical predictions are obtained by averaging the typical behavior of many nearest neighbors. And so we need to understand the distribution of different responses. As is shown here, this will include all the events which is greater than the predicted value, and this will include 70% of the events. Now, this variability of response to the solar wind driving is essentially the multiscale behavior of the magnetosphere, and we went into some detail of analyzing the multiscale behavior using the fluctuation analysis of complex systems. And this is the work done mainly with Venkat Anurag Sethi, who did his PhD research on this and submitted his dissertations on 2014. So a complex system has many features. Among them, they are non-equilibrium in nature, so it's not easy, or one cannot do a straightforward analysis of the fluctuations. And so we use nonlinear dynamical modeling, which is a data-enabled modeling to define or get a prediction of the typical conditions. And then we go to the statistical analysis or the fluctuation analysis to get a quantification of the variability. And fluctuation analysis gives us many things. One of the most convenient things is the scaling exponents, also known as a Hurst exponent. And these Hurst exponents lead to or can be used to define the predictability. These exponents of, however, they are not single exponent for a given system, it can change across the scales, and that leads to crossover in the scaling index or behavior, and that leads to further details of the nature of the dynamics. And the Hertz exponent essentially tells us the long-range correlations in the system. If there is no correlation, rather long-range correlation, and then we will have H exponents as is expressed here, which is about 0.5. So if we have Gaussian noise, it will have a Hertz exponent of 0.5, and f of t will be the scaling or the fluctuation function. And when it is greater than 1, there is persistence or memory, which can be the source of extreme events. Without persistence or long-term correlations, extreme events are very unlikely, as we know in Gaussian distributions. And the way to compute Hertz exponent are many. First thing, we have to remove trends because they lead to wrong or misleading exponents. And also we have to normalize data. Hertz, in his studies of the Nile River flood in 1951, used what is known as the Rescale range analysis, in which plot like this is of random walk using Gaussian noise. And for such a data, a range can be defined by from the lowest value to the highest value, and then the trend is a linear trend assumed, and that leads to the fluctuations after the trend is removed, and that is used for obtaining the distribution of the fluctuations or the scaling law. In the fluctuation analysis, we use a different method, the mean square deviations, and this is also widely used. However, for non-stationary data, it doesn't do very well. For Gaussian noise, this function, as we see, does very well, and in many applications, these are used for different studies. The third method, and which is more sophisticated and more complete, is the detrended fluctuation analysis, in which we take the local trends, remove them from the data, and then analyze the fluctuation function. And shown here are two frames in which the data has been divided into segments of length 100 steps on this side and 200 steps on this side. And then in this window, the fluctuation is assumed to have a certain a trend of a polynomial form indicated by p sub s to the power of n, and that trend is removed, and for each window we do the same, and then we get this fluctuation which is detrended. With a larger window, we do the same process by removing the trend, and then analysis of these fluctuations at different scales leads to the scaling index alpha, which is related to H index by this expression. And we followed techniques in Kendall et al. Paper to apply it to the AE data, and we obtained the Hertz exponent, which is about 0.8 to 9, and that indicated the presence of long-range correlation and thus of extreme events. However, we saw on further studies that the scaling in the fluctuations takes place in a more complicated way. Namely, it has two regions, one in which we have a scaling as is here, and another as is on this side for different lag times. And this crossover region tells about the physics or the nature of the fluctuations in this system. And understanding that is one of the things that we pursued. And for that, we use AL and solar wind data for about 13, 14 years, and then looked at the fluctuation functions with different detrending analysis. In this, what we see in this picture, the fluctuation analysis with a linear trend, that's DFNA1 is used, and this blue circles shows the fluctuation for log of the fluctuation function for AL index, and the red circles show the fluctuation function for solar wind. As we see here, there is a crossover, and the way to determine the crossover point is a hyperbolic regression, which I did not talk in detail here, but it was used in many other applications, which is essentially using the hyperbola with two asymptotes, one given by this line fitting to this side, the other asymptote fitting to this side of the curve. And then this is the point where is determined from these two asymptotes, and we take that as the crossover time. And similarly, for the solar wind, we get a crossover, which is around at the time scale of about a day. And as we see here, the crossover in AL index is not in the, is distinct from that in the solar wind, and it takes place at about 4 hours. And before the, or rather on time scales shorter than the solar wind crossover time, the magnetosphere or AL index has a different scaling behavior. Above that, they are more or less similar. So the broader or scaling behavior in the magnetosphere is distinct from that of the solar wind, and the crossover in the scaling of the distribution takes place at about 4 hours. And this we could develop into a model in which OU, that is Ornstein-Uhlenbeck-Langevin equation of this form, it was used, where we use the lambda or the driving or the friction term as related to the crossover that we determine from the fluctuation analysis. And if we use the OU-Langevin equation and then analyze the fluctuations using the fluctuation analysis we indicated, we get this scaling law. And if we get the AU index after the detrending, we get this distribution function. And to see whether these are noise or other effects of noise, we took derivatives of this function and look at the fluctuations, and they become flat very shortly. So these are this is the case when the fluctuations are well represented by the scaling laws. And another advantage of the crossover time is that we can use this to model the variance, and using a technique that's known as multiple trajectory ensemble, we get from the equation we had this form for the variance. And if we and this is represented by this red line, and if we compute the variance from the data directly, that's given by the dot crosses here. So they agree very well. So the statistical behavior of the magnetosphere is represented fairly well by the OU-Lanzmann equation, in which the crossover time is used as a time scale for the friction or the driving term. So with this, these studies of long-range correlation, then we can try to characterize the extreme events with the recognition that for a normal distribution, such as this blue curve here, there's not many large events, whereas for the Levy distribution, as is shown by the red curve, there are many extreme events. And in this case, we'll have H index, which is significantly larger than 0.5. And that H index can lead to thickness, of the tail, and therefore a measure of the extreme events. This is a line of work we are pursuing now, and we will now move to another way of characterizing the prediction and predictability of extreme events using the Ensemble transform Kalman filter, ETKF, in the reconstructed phase space. Kalman filters are widely used for improving predictions. We have model forecasts, observations, and then that leads to analysis, or that is a way of data assimilation. And in that process, we have the equations that provide the predictions, the model. In the case of when we do not have the equations or the dynamical equations governing the evolution, we can obtain from the data the evolution using the nearest neighbor technique that we mentioned. So we can extend the ETKF in the reconstructed phase space, and that enables study of the predictability of extreme events in situations when we have only the data. And this applies to the case of AE index. AL index is shown here, and it used the idea indicated in this picture of Lorentz attractor. Here we have ensemble, initial ensemble, which stays more or less together, another which explores more regions of the unstable or the hyperbolic region, and the case when we have some of the ensemble members reaching the far ends of the attractor, and thus leading to behavior that we would characterize as extreme events. And so the spread of the ensemble as it evolves, indicates the presence of extreme events or inclusion of large events in the ensemble. So when we take an ensemble of states and follow their predictions using the ETKF, and then examine the spread of that ensemble as the progression, as the system evolves, then we see a change in the ensemble. And in the case of AE index, what we show here is the change in the ensemble spread by the size of the dots as well as the color. So at low values, the ensemble spread is very low, and at high values, the ensemble spread becomes larger, indicated by larger circles and also by the color. So that tracks with the amplitude of the event. So this, if we call this extreme event, the ensemble spread correlates very well with the occurrence of the extreme event. So we can think of the ensemble spread as an indicator of extreme event occurrence. This is work done by Erin Lynch in her PhD dissertation, which was jointly advised by Eugene Talne and myself. And she completed her research on data-driven modeling, and this extreme event analysis is one of the areas that she contributed. With that, I would like to move to the study of solar wind turbulence as a complex system. And this follows the early ideas of understanding turbulence through dynamical systems approach, which Ruel and Tarkins initiated in 1971. And that approach led to many interesting results, but it requires knowing the dynamical equations. And for a system like the solar wind turbulence, in which we do not have even the number of degrees of freedom and the variables well known, it becomes difficult. But the data-driven modeling that I described earlier provides a way to explore solar wind turbulence as a way to using this technique or the dynamical systems approach. And in this, we construct the dynamical trajectories as we did describe before, and use these as the trend. And by removing this trend, we get the fluctuations and the scaling indices. And this work was started by Orlando Romeo during his undergraduate physics and astronomy honors research. And Orlando now is doing his graduate program at UC Berkeley. And he used the solar wind data over a long period, about 12 years. And as a beginning or first step, we looked at the timescales from using autocorrelation function, mutual information function, and in mutual information function, 2 techniques were used. And broadly, we saw that mutual information function is more reliable. Autocorrelation function, being a linear correlation, doesn't represent the system very well. And with that kind of values, the time delay vectors, the first 3 vectors, after applying the time delay embedding, is shown in this plot. We can sort of see that there is dynamical behavior. That is, these lines are supposed to show the trajectories, but this is not very clear or convincing, But if we use the SVD, which is the basis for widely used principal component analysis, then the dynamical trajectories become very somewhat clear, and in fact, quite clear in many cases. These are animations for different time delays and different embedding dimensions, and the variability or the change in the nature of the trajectories for different values of this tau and m become quite evident, which is not unexpected because the SolarWind being a turbulent system, and that too in open environment, we do not exactly expect the low dimensionality that is found in systems like the magnetosphere or the atmosphere or such systems. The variability is seen in the singular spectrum here. I'll focus on this frame in which the eigenvalues needed for reconstruction is broadly represented by the number of eigenvalues here. And depending on the time delay, in this case, we see the number changing. So there are periods of low dimensionality and high dimensionality, and that leads to a very complicated or complex prediction situation. And using these values and three nearest neighbor algorithms, and one in which the mean field is used, that's the simple averaging method, or the trajectory is used instead of the location, and the weighted mean field is used, and in all, 5 neighbors are used, and that we obtain SolarWind forecasts whose mean square errors are given by these values. They are broadly in the range of 130 kilometers per second, and the values differ in some cases, especially when we have very large dimensions, and how we obtain the different prediction techniques. And roughly, this has the distribution as shown here. I'll not be able to go into all the details here, but it is a representation of the mean square errors that we just looked at. And for different dimensionality and various techniques, the values have this range as I mentioned. And if we look at the residuals, they have various distributions which are not very consistent, except there are clear trends which can be used for providing the nature of the fluctuations. In other words, these data-driven modeling of turbulence can be used for for predicting solar wind, which can be used in prediction of space weather, and also it can be used for defining the trend so that we characterize the fluctuations in the solar wind to obtain scaling laws and other behavior. And this is an ongoing research that we are pursuing. And the next topic is machine learning in complex systems, which is widely popular now. The basic idea is to develop machine learning for dynamical systems. Most machine learning techniques are based on pattern recognition, and they are not very good for dynamical systems or situations where the systems change rapidly. And for this approach, we use neural networks in by first doing the dynamical systems modeling so that we do not know the equations or the details of the dynamics, and we use the time series and spatiotemporal and distributed data. And this is work done by undergraduate students who work at Maryland in my group. And what I show is mostly work of Adam Zuckerman, who is now at graduate school here, and Chris Croft, who is at the graduate school at Harvard. And if we look at the neural network, which using the ReLU, which is one of the deep learning machine language learning processes, stands for rectified linear unit, details of which I'm not expert on. Then we get predictions which fit the data, and the distribution is of this form. If it were a pure Gaussian, then it would indicate that the predictions are as good as it can be. However, we have this tail, and so that indicates the missing or the existence of extreme events again. And if one of the main steps in this analysis is to compare the data or the way the neural net can be used for different forms of data. One is the time delay embedding, as we saw in the SolarWinds case. That doesn't tell very well about the dynamics, but the PCA vectors do much better. And it's the same here in the neural net when we use the two cases. The comparison is given here. That is the error in the predictions for the PCA, as is in the orange, and then the blue and the orange, which is for the time delay data. So with the PCA, we have much reduced error in the predictions. And this is a project that is ongoing. We are now focusing on recurrent neural nets with LSTM, long short-term memory for dynamic systems. We have about 6 or so students, undergraduate students, whose majors are in computer science, physics, mathematics, data science. And we have many applications in a wide range of systems. The last topic I would like to come to in a very short minutes is to develop a picture or a framework for digital geospace so that we can harness the growing data in geospace or heliosphere analysis and modeling, and to create a digital twin of geospace so that we can look at the phenomena in geospace along with the development of large-scale numerical simulations. As many of you would know, there is a effort in atmospheric science, Earth system science community to develop digital Earth, and this paper by Bauer et al. Provided a very convincing picture of the need for such a system. And one of the ideas is that, or reasons, is that purely physics-based modeling approach requires so much computational power, it is limiting timely analysis. So we need to develop alternative ways to reach the our goals in analyzing and understanding these systems. And machine learning AI approaches, they take advantage of massive amounts of data so they can be utilized well. And in space weather, we can use it for developing near-term predictive capability for space weather. We have been pursuing this kind of thinking for some time in the form of perspectives, as is shown in this one, also in the form of proposals to more than one agency, of course, not funded. And I think we should look at this approach of developing a combined system in which we combine the data analysis and modeling so that we can develop better predictive capabilities. So in summary, data-driven modeling in complex systems framework provides the underlying dynamics, it gives predictions, and has a way to provide the quantitative predictability. And as was recognized in the atmospheric science community, physics-based modeling alone may not be enough to provide timely and detailed understanding of the complex systems. And the complex system approach provides a comprehensive framework for putting these together. And digital geospace, as I just indicated, is a pathway to improve space weather prediction capability in the near term. I would conclude by expressing my gratitude to David Sivak, Kyle Murphy, and Jason Schuster, organizers of the AGUSPA Magnetosphere Seminar Series. And I'm thankful to all who do me the fair honor of listening.
Excellent. Well, thank you very much, Dr. Sharma, for a fascinating presentation as well. And there are certainly some questions to jump into here. I actually thought I would start out of order with the last question because I think this slide sort of summarizes it nicely. Looks like Stephen was wondering about this idea of the digital twin for geospace and perhaps just a little more on the motivation and how we could improve those space weather predictions with such a digital geospace.
Mm-hmm. Yeah, of course, it is a combination of many things that we like to have in the digital twin. First, if we have a numerical model, then we can use that to predict or understand geospace or the Earth system. But the Earth system doesn't have such a model. And we mentioned in the beginning of the talk that the Earth system is about, the atmosphere is about 10-kilometer size. And even modeling all the processes, the multiscale from the size of the cloud to the weather and beyond that climate is not likely to happen with just numerical models. So we need to combine what is available from the data and also the simulations using various techniques so that we put them together, and then that will give us a way of providing predictions as well as the understanding of the system. The basic idea is to make the best use of the data we have, the observational as well as from the simulation. There are a lot of challenges to that, of course, and a lot of steps or processes that we need to define. But the basic idea is to define a framework in which all the data will be put, and then use that to fill the gaps where we do not have either the data or the simulation.
Certainly, yeah, excellent response. That actually segues nicely to the next question that Ryan McGranigan just asked. And first, he just makes the comment to thanking you, Surja, for that vision of the digital geospace. It certainly is a compelling one. And Ryan was wondering, in particular, he was curious what you might see as maybe the composition of a team or even a community that's needed to really achieve that goal. With also a link he included for an upcoming AGU session, so the SPA session as well. But yeah, what would be your thoughts as far as some next steps or even a team-based approach to this problem?
Yeah, I think we should move ahead with the idea of a team and formulating what we should do. So on the way to such a goal, the Earth System Science community has had meetings, workshops to define these, and I was part of at least one of the meetings, and we can learn from that. And of course, learning from the atmospheric or Earth System Science community is a bit complicated. We have to be careful of the scales. As I mentioned, the atmosphere is about 10 kilometers thick. That's about the thickness of a dollar bill if you think of the Earth as the size of a globe that we used to have, about 1 foot or something like that. Whereas the geospace is millions of kilometers. And we have the unenviable situation in which we have many models, plasma models, starting with kinetic, as Jason would know, and going to ideal MHD. So the task is a bit more complicated for us for developing predictive numerical pathways, as well as for the geospace digital twin. So the first effort will be to recognize the data and how we can put it in a framework. And I think the complex systems framework is a good framework, but this needs to be discussed. So for forming a team, I think we can definitely go ahead and form a team. Then AGU session, etc., will be interesting, but I think an open discussion would be the first thing that would be very preferable for this.
Mm-hmm. Great. Yeah, thank you for that response as well. And let's see, just going back into the chat. So Kyle also was wondering, in some of the earlier slides, what physical processes lead to the different time scales in the solar wind for the AE and AL indices? And is the difference between typical and extreme events associated with different physical processes or drivers necessarily?
Yeah, so Kyle, when we say physical processes in plasma or plasmas, we think mainly of normal modes and their couplings at different scales. And if we try to see what waves are important among the normal modes, in solar wind, it is typically alpha waves. But normal modes are linear modes. We know them as solutions of linear Sturm-Liouville equations or simplified equations. Coupling between them leads to either more complexity or shorter scale processes or large scale processes. So understanding how all the modes interact together and lead to some particular scale in a dynamical fashion, that is following a certain mode, how it grows, how it couples, and how it interacts with other modes, is not very practical. That's why we take the view of separating what can be understood in the dynamical sense and what's beyond that, nature of the fluctuations. In fact, that is the basic thinking of dynamical systems approach to turbulence. We know turbulence is very complicated. We cannot follow how a certain vortex in a river flow will move and become either larger part of a larger vortex or break into smaller cascades. So the scaling laws become clear, but scaling laws doesn't tell you what will happen and at a certain time or how it can be followed. So by using the dynamical systems approach, we can develop picture of the different scales that develop, whether it is Alfvén waves or Whistler waves. I do not see a direct way to do it. And that is what we mean by saying purely physics-based modeling approach requires a lot more computational power. I do not know if we have that computational power, and even if we have a way to reach to that conclusion. I may sound pessimistic, but knowing all the things that is involved in the evolution of the solar wind or seeing the different kinds of interactions, I do not think we are close to identifying what plasma processes lead to formation of structure in the solar wind of a certain size. We can do it from the statistical, dynamical and statistical point of view, in which we can say about the evolution of such system sizes and the likelihood of such systems. That is the dynamics and the predictability. That's my view.
Mm-hmm. Very good. Yeah, thank you for those considerations for that one. And let's see, so the next question, just to squeak in a few of my own questions. I was curious specifically back on slide 16, I believe it was, and some of the particulars of the methodology. I think, Surja, you were mentioning the detrending that's needed for many of these models. And I think on that one, you mentioned that that was a more sophisticated approach where you actually detrend based on a polynomial of an arbitrary, this is the slide, I think.
Yeah.
And then so that p to the s sub n. So I wondered if the n, is there a maximum, say, polynomial of degree 3 or 4, or how large can that n exponent be when you do the detrending in this method?
That's an excellent question, and thank you. This is one area where we are able to provide a new technique. First off, n is the order of the polynomial. So it can be a constant, a linear, a quadratic, quartic, and so on. So how do we decide which one should be used? There is no real or physical way to decide that. So one uses, say, a quadratic, as is shown in this picture, and see if it works, and go to quartic and so on, and see if things change. If the nature of the distribution or the scaling doesn't change, then we become satisfied or convinced that, say, the lowest order, for example, quadratic in this case, works. However, this is not self-consistent and not very satisfying for theorists. So what we have tried to develop, and Seti developed this to some degree in his PhD thesis, is to use the predictions from the data-driven modeling, the reconstructed phase space, as the trend. Then we do not have to assume a polynomial as here. The polynomial is replaced by a trend defined by the data itself. No ad hoc assumption of the form of the polynomial, and consequently the trial of trying to find the best suitable form is not necessary. It doesn't come in the picture. So that's the way we think it can be done better. So most of the cases, one just tries different polynomials but we have a way, I think, to improve the way of doing detrended fluctuation analysis.
Certainly. Yeah, thank you. Especially the thesis work. It sounds like a very promising way to proceed with that technique. So, okay. Well, with that, I think that comes to the end of the presentation. And in the comments, you can see there are definitely some compliments, and those are very appreciative of the talk, as are we as the hosts. So thank you again, Dr. Sharma, for your presentation, especially in light of the recent Nobel Prize news. It was exciting to kind of connect the dots with our magnetosphere and the complex systems perspectives. And so with that as well, I'd like to mention this does bring us to the end of our calendar year for the seminar. So we won't have a seminar for next month, in part because of AGU preparations and also with the holiday season. But do certainly stay tuned for more programming coming and more things we have planned in store for next year. And stay tuned to the newsletters and email updates from Kyle and David and myself for that. So again, yeah, thank you again, Surja, for today, and we appreciate
it was
everyone's
my
time.
pleasure. Yeah. Is the text of the chat and Q&A available?
Yes, it is. I can certainly send that to you afterwards, so we have a record of the questions.
Since I did not get a chance to look at them.
Sure. Yep, not a problem at all. Okay, great. Well, thank you again for your time, and thanks everyone for tuning in. So we'll see you next year.
Hey, thank you.
Okay. Yep.
Thank you, everyone.
Thank you.